Okay, welcome to today's explainer. We are going to completely demystify the arrangement of a polymer extrusion line. We're taking what might look like a bunch of dry, boring schematics and turning them into a dynamic, logical tour of the factory floor. So if you want to understand how to efficiently manage, lay out, and organize real-world manufacturing operations, you are absolutely in the right place. Let's get into it. To really master how these lines are arranged and managed, we're going to follow a very specific path today. We'll start with an overview of extrusion, move into the extrusion line layout, then cover feeding and plasticizing, shaping and curing, and finally, optimizing operations. Basically, we're tracking the material's entire journey from raw input to finished product. All right, Section 1, Overview of Extrusion. Let's quickly cover the absolute basics of what makes this technology so critical. Now, the absolutely crucial word here is continuous. Unlike batch manufacturing where you can stop and start, a continuous line demands rigorous spatial and operational organization. Think about it. If even one tiny part of your physical layout is arranged poorly, the whole continuous flow just breaks down. And that hits both your productivity and your product quality right where it hurts. Moving right along to Section 2, the extrusion line layouts. Let's explore how this actually translates to the physical factory floor. As a line manager, your theoretical blueprint maps out a beautiful straight-line journey. You've got your raw fiber bundles organized on the far left, feeding perfectly into a liquid resin bath, pulling through the shaping and curing stations, all the way to the cutting knife on the right. It is a perfectly logical, orderly flow of operations. But as we all know, bridging the gap between theory and actual factory management is where the real work happens. Out on the floor, managing the pulling system gets intense. You might be dealing with 10 distinct bundles of e-glass, fiberglass all at once. Managing that layout means you have to ensure all 10 bundles feed smoothly and continuously, completely tangle-free before they even get near the resin. And it doesn't stop there. Further downstream, you hit the curing station. To properly arrange this, you need some serious floor space because you're dealing with a massive 12-meter-long continuous heating tube. Seriously, that is roughly the length of a standard city bus parked right in your line. You have to purposefully design your factory layout around this massive footprint, just to ensure rapid, continuous hardening. So on to Section 3, feeding and plasticizing. Let's dive into the critical first stages of material prep. A highly effective line manager doesn't just look at the machine as one big monster. You have to arrange your operations rationally by breaking that continuous flow down into 3 distinct stages: mixing, shaping, and curing. Mentally structuring the line this way allows you to isolate variables and fix problems super fast. And in that very first step, the chemistry has to be as highly organized as the machinery. We're talking an exact 65 to 35 ratio of e-glass fiberglass to epoxy resin, plus a highly controlled dose of an adjustable curing agent. If you don't manage this precision at the feeding stage, literally everything that follows is compromised. This next part is a brilliant example of cause and effect in line layout. You absolutely must physically place a filter screen right before the shaping die. It's basically your VIP bouncer, catching any unmelted solids or impurities. If you sequence this wrong, those solids slide through, cause blockages, create massive pressure spikes, and totally ruin your product. Which brings us to Section 4, shaping and curing. We've officially reached the critical bottleneck of the layout. Listen, if the internal walls of your shaping die aren't polished to a mirror finish, or if the geometry has sharp corners, you are in for a bad time. The flowing polymer will literally stall out in those corners, which totally degrades the surface quality of the final product. It is exactly like a traffic jam at a sharp highway turn. Smooth, continuous curves are absolutely mandatory to keep the flow moving. Then, as the material shoots into that 12-meter heating tube we talked about, you face a crazy, delicate temperature balance. Go too hot, you're going to burn or evaporate the epoxy resin. But actually, if you go too low, the composite bar exits the tube soft, uncured, and structurally useless. It's a real Goldilocks situation. And that leads us perfectly into Section 5, optimizing operations, the ultimate balancing act. Let's talk about pulling speed. It's arguably the most dangerous variable on the floor. If you manage it poorly and pull too slowly, your factory productivity just tanks. But if you get greedy and pull the material too fast, only the outside surface cures. You're left with a core that's totally soft and completely defective. So, imagine you're the engineer standing on the factory floor, staring down this massive, complex line.
how do you mathematically figure out the exact perfect pulling speed? Because I'll tell you right now, simple trial and error is just way too expensive.
The secret is finding what we call the operating point. This isn't guesswork at all. It's a precise mathematical sweet spot where your shear rate, your temperature, and your pulling speed all perfectly align. True layout mastery means setting up your equipment so you can consistently hit this mathematical bullseye every single time.
The math proves this perfectly. If you dial in a specific pulling speed, let's say 15 meters per minute, that single decision directly dictates the volume flow and the shear rate inside a very specific section of the die. Every physical adjustment you make on the floor instantly ripples through and changes these underlying numbers. And when you finally hit that sweet spot, the results are wild. When a manager successfully arranges the line, balances the tricky chemistry, and locks into that optimal operating point, experiments show they can hit a maximum tensile stress of 564 newtons per square millimeter. That is incredibly strong.
Ultimately, what mastering the layout and optimization of an extrusion line teaches us is that true engineering is really just about bringing physical order to chemical chaos. By logically arranging the factory floor, strictly controlling the continuous flow, and dialing in the math, you create flawless products. So armed with these layout management skills, what complex process will you optimize next?